Welcome to today's session. We have been discussing about interference in thin film for few sessions. We have already seen interference in a variable thickness wedge-shaped film. Yet another example for fringes of equal thickness is Newton's ring. In this session, we will see Newton's rings and its applications in details. So let's begin our session. Take a plain glass plate. Place a plane convex lens with its curved surface in contact with the glass plate. This arrangement will result in a circular air film of thickness 0 at point of contact R center and equally varying thickness in all direction outward from center. Now illuminate the setup with monochromatic light from the top. If we focus the traveling microscope at the top of the setup, we can see concentric rings, central dark and SND alternate dark and bright rings. These concentric circular fringes was first observed by Sir Isaac Newton and hence named as Newton's ring. Depending upon the phase difference between the interacting rays, we may get a dark or bright circular fringe. So, our next step is to get an expression for optical path difference between reflected rays. Just look at the diagram. The ray C incident at the point D, is partially reflected from the upper surface of air film and refracted along point J as ray 2. At J there is air to glass boundary. The refracted part of ray C, now reflected at J, suffers a 180-degree Hazer change and travel as ray 1. Since ray 1 and 2 are essentially coherent rays from a single ray C, so they will interfere to give fringe. Optical path difference capital delta is 2 mu t cos a minus lambda by 2. For bright circular fringe, path difference must be m lambda. On equating and rearranging, we get expression for path difference for bright fringe as 2 mu t is equal to 2 meters plus 1 lambda by 2. For m changes 0, 1, 2 etc. Similarly, for dark circular fringe, path difference must be 2 meters plus 1 lambda by 2. On equating and rearranging, we get expression for path difference for bright fringe as 2 mu t cos r is equal to m plus 1 lambda. Since phase relationship of interfering wave dose not change of one full wave is added or subtracted. So, may write m for m plus 1. 2t is equal to m lambda. For m changes 0, 1, 2 etc. We can derive an expression for radius of circular fringe as follows. Let us consider our Newton's ring setup. Let's take the plano-convex lens of large radius of curvature capital R. Q be the month's dark fringe of radius Rm that correspond to T thickness of air film. From the figure, we have OC equals Pn equals Rm, MO equals Pm equals capital R. Consider triangle MNP. By Pythagoras theorem, we can write a square equals Rm square plus a minus T square. On simplifying, we get our m square equals 2RT minus T square. Thickness of air film T and hence T square is very much less than 2RT. Since we already mentioned that radius of curvature is very larger. So, ignoring the T square term, we get expression m square equals 2RT. We can write radius of month dark fringe as m equals square root of 2RT. We can also write radius in term if wavelength of light. Since Q is the nth dark fringe, we have condition for dark fringe 2t equals m lambda. On substituting this equation in expression for radius, we get square root of m lambda r. That is, radius of the month dark ring is proportional to the square root of wavelength. We can write expression for diameter of month dark ring as 2 times radius, which is 2 times square root of m lambda r, or 2 times square root of 2rt. Do you remember when we saw fringes of air wedge, they were equally spaced? So let's check whether the fringes pattern we observe here are equally spaced or not. For this, we just need to check whether the distance between two consecutive dark rings are same or not. We already know the expression for diameter of month dark fringe. So we just substituted m as 1, 2, 3 and 4 and we get their value as 2 square root of lambda r, 2.8 square root of lambda r, 3.4 square root of lambda r and 4 square root of lambda r. Look at them closely. Is the difference same? No, not at all. Not only they are equally spaced, but also the difference is decreasing. That is, as we move from center dar fringe to R-ward, the rings move closer and closer. This is why the observed rings are not evenly spaced. Look at the image of circular fringes observed. These fringes are fringes of equal thickness. Each fringe represents locus of points corresponding to equal thickness. Hence, the fringes observed are fringes of equal thickness. Now, we have seen the theory. Now we will see how we do it practically in lab. Look at the diagram. The experimental setup is shown right there. Take a plain glass plate and place a plano convex lens with curved surface in contact with the glass plate. The source of light S is switched on. The light is made parallel by converting lens. The light is made to incident on a glass plate inclined at 45 degrees with respect to horizontal plane. Light reflected from this plate falls normally on lens glass plate system. Rays reflected from top AMD bottom surface of thin air film will interfere and we see concentric rung of alternate dark and bright fringes on traveling microscope. The cross wire is made to coincide on MTH dark fringe on left side of central dark fringe and reading is noted. Readings are taken corresponding to different dark fringe till the cross wire reach month dark fringe on right side of central dark fringe. Difference between corresponding reading of month dark ring on right and left reading gives diameter of month ring. Now we have a set of readings. We can determine wavelength of light source using this setup. For month and m plus pth dark fringe, we can write diameter as dm square equals 4 meters lambda r. dm plus p square equals 4m plus p lambda r. Taking difference we can write dm plus p square, dm square equals 4p lambda are then wavelength lambda equals dm plus p square, dm square divided by 4pr. We plot a graph taking diameter square along y-axis and m along x-axis, we get a straight line as shown in figure. The slope of line gives dm plus p square, dm square divided by p. We can easily determine radius of curvature of lens using spherometer. Knowing r and slope of graph we can determine wavelength lambda as slope slash 4r. Yet another application of Netwans ring is to determine refractive index of liquid. For this we have to place a drop of liquid between the lens, glass plate so that a film of liquid is formed instead of air film. Recall that when we derived expression of path difference we took mu as 1 since we considered air film there. Here, since it's a liquid film of refractive index mu, there appear a mu term in expression for radius. dm square equals 4 meters lambda are divided by mu. As earlier if we write expression for difference of square of m plus pth and month ring diameter. For liquid film dm plus p square, dm square equals 4p lambda are divided by mu. And for air film dm plus p square, dm square equals 4p lambda are taking ratio of both we can write expression for refractive index of liquid mu as ratio dm plus p square, dm square for air divided by dm plus p square, dm square for liquid. Experimentally, we will do the entire procedure with air film, take reading and find dm plus p square, dm square for liquid. And then repeat same procedure with liquid of unknown refractive index between lens and glass plate. Take reading and find difference between square of diameters of same dark fringes. The ratio of difference gives refractive index. So, in today's session we studied about Netwans ring. The fringe pattern we get in this case will be concentric alternate bright and dark rings that moves closer and closer as we move from central dark fringe to outward. This setup can be used to determine the wavelength of the incident light and also the refractive index of the unknown liquid. In next class we will discuss about Michelson's interferometer. Thank you for today. See you in next session.